Today is given by Professor Kefeng Liu from Chengqing University of Technology. The title of this talk is Intersection Theory on Modular Space of Super Riemann Surfaces. As well.
First, I'd like to thank the organizer, especially Professor Yao, a chance to talk on this huge conference. For the past many years, I have been working on moduli space, and especially this beautiful moduli space of Riemann surface on the geometry and topological aspect. So the intersection theory on such moduli space is closely related to physics, especially some a big progress actually on the study of this moduli space. It's motivated or inspired by physicists, okay, especially the work of Weil. Okay. So let me start with some basic notions. By the way, yesterday I think Professor Jian Zhou gave a more extensive talk about the relations of the intersection theory on moduli space to various aspects for physics, especially statistical physics. Okay. So a compact Riemann surface is a one-dimensional complex manifold. Of course, it's a two-dimensional real manifold over complex numbers. Its topological type, okay, up to diffeomorphism, is uniquely determined by the genus. For example, one of the most I think beautiful theorem is the Riemann uniformization theorem. Okay, it's about the Riemann surface. And the genus 0, genus 1, one whole, and genus 2, and so on. Okay, so G can go to infinity. So we consider, for example, the famous Fermat curve for any n bigger or equal to 1, an integer. Planck curve in T2 given by this x to the power n plus y to the power n equal to z to the power n. This is one of the compact Riemann surface. It's an exercise we did when we were graduate student. The genus is half n minus 1 minus 2. Okay. So even if we only interested in moduli space of curves, but to compactify it, we need to study moduli space with marked points. Okay. So in geometry, differential geometry, like to study moduli space with boundary, but in some sense they have some common features, as we will see. So the boundary, the compactification, okay, so possible Riemann surface has this geometric computation compared to higher dimensional, which is a very difficult job for algebraic geometers for higher dimensional complex manifold. Okay. So we consider a Riemann surface with a marked point. For example, this is a Riemann surface with a specific point. Two of them, we have these operations which we can glue them. Okay, glue the two marked points, get a singular Riemann surface. Okay, so this is a singular point. Of course, you can go the other way, and you can shrink a high genus Riemann surface, shrink the circle. Okay, so you get a singular Riemann surface. So that's how we get the boundary. And similarly, you have two marked points of genus 2 curve. You glue these two marked points, you get a genus 3 Riemann surface, but with a singular point, okay, with a cusp. So here, we consider a Riemann surface with 4 marked points, because modular space always regular automorphism. So therefore, we can always use the automorphism group P1 to fix 0, 1, and infinity, these 3 specific points. We allow the actual point to move. Of course, we get CP1, P1 minus 3 points, because this Q can freely move on this space of 3 puncture sphere. Okay. In particular, when Q approach 0, okay, so you get a singular, you blow up actually you get a singular curve. When Q goes to 1, goes to infinity, you get these three singular curves compactified this moduli space to P1. Okay, so that's how it goes. Okay, so there are some very important characteristic classes or Chern classes on the moduli space of Riemann surface with marked points. Okay. So in 1983, Mumford wrote a long paper to initiate the intersection theory on moduli space of Riemann surface. In particular, he studied the so-called tautological classes on the moduli space. The first class is a psi class. So we consider a line bundle. And the line bundle, that means the cotangent line of the marked points. So when a curve moves on the moduli space, of course, you get a line bundle, complex line bundle, actually holomorphic line bundle. The first Chern class of i's marked points, that's the psi class. So you consider there's another natural line bundle, the Hauger bundle. So that's the space of holomorphic one forms. And that's a dimension G holomorphic vector bundle. You consider is Chern classes, you get G of them. Of course, the first, rigorously C0 equal to 1. So you C1 to Cg, and you get these Chern classes of this Hauger bundle. Okay. And another one is called the Kappa class. Okay, so Kappa class is the push forward of the class on actually there's a natural forgettable morphism, or you can consider this as a universal family. Okay, MGN. You consider MGN is universal. It's a fiber. It's a genus G+1 class. You can forget the I+1, the marked points. You get a forgettable morphism. You push forward the I+1, say I+1, okay, to the I+1 degree. You get this. Of course, it's another tautological class called the Kappa class. So it's produced from this psi class. Okay, so I think both mathematicians and physicists are interested in the integral of psi classes. Okay, so this is called the descendant integrals. Okay, so the notation is I think this is from physicists. We consider tau d1 to tau dn equal to the integral over the moduli space for n marked point. You have n the psi classes d1 to dn. Okay, so of course the top degree should match the dimension. You get the integral. And so there are some well-known or relatively simpler equations for this integral. The first one, you take d1 equal to 0, and you get actually get this relation. Okay, and Dilaton equation, this is string equation. Dilaton equation is tau 1. Actually, you can integrate over the fiber to psi 1, and that's the Chern class with puncture, n puncture, and like you get 2g minus 2 plus n. And so you can actually, this can be integrated out. Okay, so that's the first one, you get a recursion. So let's integral psi classes. There's this, I think, one of the nice work for Wolpert. He proved this nice formula, the Weil-Petersson symplectic form. Okay, so that's the Weil-Petersson symplectic form is the natural L2 inner product on the tangent space of moduli space, which is H1 for the tangent bundle. Okay, from Cordelia-Spencer theory, it's H1 tangent bundle of the Riemann surface. Okay. And this formula, omega gn, is a Weil-Petersson symplectic form, is equal to 2 up to 2 pi square equal to kappa 1. It's the previous integral kappa class, tautological class. So therefore, we can consider this integral of kappa classes, which is the same as the integral of Weil-Petersson volume up to a normalization factor. This is called Weil-Petersson volumes. Okay, so this is both mathematicians or physicists are very interested in the calculation of this volume, of course, but it's very difficult to get a closed formula. So even recursive formulas are not easy to get. Okay. And also another interesting topic is to consider when g go to infinity, n go to infinity, the asymptotic behavior of this integral. Okay, so that's still under intensive research. So here, in 2000, Manning and Zograf proved VGN, when n go to infinity, asymptotically, can be calculated. Okay, the leading term is given by n factorial. The constant c, capital C is actually, it's people trying to prove, okay, it's c equal to 1 over square root of 2 pi. Okay. And then a constant ag plus on, this is constant only depend on g, and then up to 1 over n terms, lower order terms. Okay, and Penner and some other mathematicians in 2001 proved this volume is bounded between these two constants, okay, up to 2g factorial, okay, some constant c. And one of famous work of Majahani and Zograf in 2011, they proved that when n fixed and when g goes to infinity, this volume is given by the leading term. Okay, so c is given by this constant. It's needed to be proved, and these are factors. Okay, and square root of g over the denominator, and of course this 2g minus 3 plus n factorial and 4 pi squared for the power, and 1 plus leading terms 1 up to this constant, then the expansion of G inverse in terms of G inverse. Okay, so that's so in principle we can only get the leading term. Okay, the other terms, lower order terms, needed to be calculated or proved yet. Okay, so we can only get this Cni, this coefficient, to be a polynomial in n of degree 2i. Okay. So even this leading constant, people conjecture to be 1 over square root pi, and it's not proved yet. So one of the, I think, so-called Witten conjecture and the concavity theorem is given by this the intersection theory is related to the KdV hierarchy. So the KdV hierarchy is the following hierarchy of differential equations. Okay, this PDE, partial u over partial Tn equal to partial over partial T0, Rn plus 1 for any n bigger or equal to 1. And here Rn are differential polynomials for the derivative for u. Okay, they defined recursively by the first one, R1 equal to u, and so on for Rn plus 1, and in terms of lower order Rn, and to be calculated. And so we can compute Rn recursively, for example, from this recursion. So this is so-called KdV hierarchy. Okay. So this dot means the derivative, I think, with respect to T0. So it's a remarkable discovery. I think a very important development, because when Mumford introduced the theory of intersections on moduli space, people can only calculate some lower genus, very low genus cases. But Witten, motivated by physics, he 2D gravity and by two different models. Okay, so he introduced these generating functions of psi classes intersection numbers. Okay, so here the coefficients are given by the intersection numbers. Okay, we introduced before and introduced infinite number of variables. Okay, up to this, you get this a huge generating series. So this guy is a tau function of the KdV hierarchy. That means it can be calculated recursively by using KdV hierarchy, as in the previous slides. So it's very difficult to calculate the integrals of tautological classes on the moduli spaces. Of course, now there are many different proofs by different people. Actually, we can give at least 3 or 5 proofs of this theorem. From different point of view, now has a much better understanding of this theorem. Okay, but the first proof, of course, by Konchevich, using matrix model and array functions. Okay. So now it has many different people, different group of people studied from different point of views, combinatorics, and yesterday Jianzhou gave a talk about this guy related from emergent geometry and statistical physics, related to various minimal models in physics. Okay. So equivalent form of Konchevich-Witten theorem is the following recursive formula given by the 3 physicists. Okay, that graph Wallinde brothers. So that means we consider the tau integral, okay, psi integral of this over mg of genus G moduli space, and with n+1 mark point, for example. Then you can get recursively reduce to either less classes, psi classes, or less genus, lower genus. Okay, so these 2 terms. Okay, so that's corresponding to 3 components of the boundary. Okay, so actually, this recursion is built on the geometry of the complication of the moduli space of curves. Okay, or equivalently, how the Riemann surface degenerate in 3 different ways. So it's naturally encoded there. So this DVV formula, you can effectively, in principle, effectively calculate all the integrals of the psi classes. So let's, as I mentioned, so there's the recursive, the pattern is built in the moduli space. So the typical recursion is this universal pattern can be illustrated by the 3 ways of removing a pair of points. And of course, this pair of points can be shrink. You can shrink the boundary into a point. Okay, so you can. It's very. So you cut. For example, you cut this Riemann surface with 2 boundaries. You cut it. You get 2 more boundaries. Okay, you get you cut these 2. Okay, so you get a lower genus and 1 actual mark point. And you can cut removing a pair of points. Removing this pan, you get this Riemann surface lower genus with 1 actual mark point. And you can remove these pans, you get get 2 lower genus and lower less number of mark points. Okay. And similarly, you remove this here. Okay, and you get same genus with n-1 mark point. Okay. And of course, this is also corresponding to your shrink this loop. Okay, and in a similar way, where you can glue this pan together to get higher genus. So let's back and forward. Okay, so here, Hao Xu and myself, a few years, actually recently, we proved this polynomial property, which we're still trying to understand. This is kind of very interesting. So we consider any, for a fixed set of integers, d1 to dn, non-negative integers, we consider the psi integrals, okay, on the top, and the ratio over the psi integrals of tau 3g minus 2, okay, and up to these factorial numbers, double factorial, okay. And it turns out that each of the psi integrals, because the modular space is orbifold, any integrals of these characteristic classes, you get rational numbers. But it's amazingly that the ratio, they are polynomials with highest degree term, 6 to the norm d and g to the norm d. That means this norm d is the sum of all these di's. And what's quite interesting is that as a polynomial of g of this degree, top degree of this guy, and it's integer polynomials. So that means that all the coefficients are integers. Okay? And of course, in geometry, we know that to understand something is an integer, you use index formula or Riemann and to identify it to some, the kernels or index of some operators. But here seems to be not easy to identify because you also get integers. Okay, if G is an integer, you get these are all integers. So both numerator, denominator are rational numbers. The ratio you get integers and as a polynomial. For example, so here we calculated some particular examples. Okay, so P1G, we'll take 1, you get that. So here you take G is equal to 3, D equal to 3, the others only 1 D, as you get this polynomial. You see the coefficient, all these cases, they are all integers, okay, integer coefficient. Okay. And here, you, for example, it's not easy. If you put 2 here, you have rational numbers, but G minus 1, G minus 2 give you integer. So clearly, this is a non-trivial fact. Okay. So, and our proof is by using induction, using the previous dVV formula. Okay. And so, also interesting to note that this one polynomial it contains information of infinite number for intersection numbers. Okay. And so Fandi, I think in a couple of years, he identified this polynomial, because any polynomial, integer valued polynomial can be identified as some counting of lattices. So let's follow from Eilhart theory. So we consider in RD an integral convex polytope. Okay, so that means integral means the vertices. Okay, are all integer numbers, integer coordinate. Okay, so you consider convex polytope of these vertices. You consider the scaling for this polytope by G, and you count the integer point, lattice point inside this convex polytope, scaled complex tuple. And the Eilhart theory tells that this guy, this integer polynomial, is a rational polynomial in G of degree D. Okay. So by using our result, Fandi found a remarkable formula of these intersection numbers as counting lattice point of certain polytopes. Okay. So basically, we used this result to do that. So that's and so here about asymptotics for these intersection numbers, we have the following result. Okay, so few years ago, Hao Xu and we proved that by using the polynomial property, we proved that for any fixed d equals d1 to dn, and this when g go to infinity, these intersection numbers actually asymptotically, the leading term, okay, asymptotically given by this top degree term and divided by these combinatorics numbers. Okay, and so this result was generalized later. Okay, actually by a conjecture by these four mathematicians, Drograph and Tao. They conjecture that when g go to infinity, for any, here we have fixed d1 to dn, but here for any d1 dn, you have this asymptotics, but uniformly in d1 to dn. Okay, so, and this was proved by Agavo by using combinatorics and the probabilistic technique. So this a different proof given by Guo and Yang. So as application, they get large genus asymptotics of major Weech volumes and the Siegel-Weech constant. They can also obtain the Siegel-Weech constant. Okay. And I think Dawei Chen and Di Yang, they also have done some interesting work on the major Weech volume and intersection numbers are modulated with the curves. I think Dawei will give a talk maybe tomorrow or sometime. Okay, now we consider Witten's R spin numbers. Okay, so this is introduced also, I think Witten generalized his theory of this conjecture, previous conjecture on ordinary moduli space. He introduced actual class. Okay, this actual class is given by taking R's roots of certain divisors by combining the certain the marked points and the canonical line bundle on each Riemann surface, and then we consider the holomorphic sections. We get a holomorphic vector bundle. We consider top chain class, and then put them together. You get a product. You can integrate on the so-called R-spin moduli space. Okay, so that because you need to go on to the finite cover to allow this divisor to be divided. You can take R's roots. Okay, so you get a finite cover over the ordinary moduli space, MGS. So this guy is a finite cover of the ordinary moduli space, R-spin moduli. Okay. And then you can consider these more complicated intersection numbers, and this turns out corresponding to other more other physical models, as Jianzhou mentioned yesterday. Okay, other minimal models, 2P and so on. So R equal to 2 exactly corresponding to the ordinary model, ordinary moduli space Riemann surface. So the generating function of Witten's R-spin number satisfies the Gelfand decay hierarchy. So this was also conjectured by Witten and was proved first by Faber and his collaborators, and later on, from different point of view, by Fan and his collaborators. So some of the asymptotic behavior of Witten's R-spin number was proved by Dubrovin, Young, and Jackiw, and also by Einard, Garcia, and some other their collaborators. So actually, for R-spin numbers, we also noticed that this polynomial property we proved for the generating series of this guy holds only for R equal to 3 and 2 and 3. And for R bigger or equal to 4, it fails. Okay, so that means it also fails for Gromov-Witten invariant, okay, even for CP1 as well. So the polynomial property is very rare in a subject. Now we consider the famous work from Zakani's recursion formula. What she did is she considered a moduli space with of Riemann surface with boundary. Okay, so she allows the boundary as a geodesic can change its length, so you get a larger moduli space. Okay, so the formula, I think the fundamental formula she obtained is this guy, this moduli space MGNL, or you have a similar Weil-Petersson volume. Okay, Weil-Petersson form, you can integrate, you get a volume form. Okay, and it's given by this recursive formula. Actually, that's the satisfy universal pattern we mentioned of the geometry for moduli space, how to compactify them. Okay, so to the lower genus, okay, a lower genus case, and Gn minus 1. Okay, so and also G minus 1 n plus 1. Okay, so that means you depend on your cut out different paths. Okay? And the kernel function is given by this hxy is given by this function, okay? 1 over 1 plus ex plus y over 2, and xy minus y over 2. Okay? So this is naturally actually over Taurus case. I think it was proved Maxent before, and but Zakani generalized to higher genus, and from there she got this formula. Mullis and Safnuk, they derived a recursion formula from Zakani's formula, okay, and derived the following formula. She considered so up to double factorial to d1 plus 1 and tau dj and kappa 1 to the a, okay, over g. So here you see from the DVV formula, there's an actual kappa 1 to the power a, okay, to so the integer a. And turns out that there's also a satisfied recursive pattern Okay, and two lower genus G and genus G minus 1 and G1 plus G2. So that means how you cut the Riemann surface, okay, into different, 3 different patterns. And of course, set has the same type of integrals, only involve kappa 1. Only involve kappa. With this constant beta given by this theta values, values of theta function. Okay. This, of course, also for the theta function at even integers given by Bernoulli numbers. Okay, so these Bernoulli numbers. So you get this recursion formula. And the coefficient, complicated, but I think only needed to remember the universal pattern. That's more interesting. So in her thesis, Mirzakhani applied her recursion formula to give a new proof of Witten conjugate theorem and obtained polynomial growth of simple closed geodesic on hyperbolic surface. Mirzakhani's recursion formula was crucially used in Mirzakhani-Zograf's large genus asymptotic expansion of Weil-Petersson volumes. Of course, also this was our work was also used crucially together with Stowe and Norbury and my work with Hao Xu. Okay. Actually, we later proved that Mirzakhani's recursion formula, all the information about the intersection numbers are the same. Actually, are the same as the Witten's recursion formula. You cannot get more than what Witten's recursion formula can give you. Okay. And they are large asymptotic, Mirzakhani and Zograf, they are large genus of asymptotic, gave a we mentioned before, can be applied to study large genus geometry, the asymptotics, the large genus geometry moduli space. For example, the distribution of first eigenvalues, systoles, and diameters with respect to Weil-Petersson measure. Okay, so Yun Hui and his student did a very interesting and important work on this subject. Now, recursion of higher weighted Weil-Petersson volume, that's what we did for the ordinary moduli space. So that's what we did a few years ago, and was crucially used in Jian Zhou's work, as he talked yesterday. And here is the formula. Okay, we consider a sequence for integers, okay, and non-negative integers actually. Okay, and so we consider the notations, the normal for m, okay, and as a vector, normal for this vector is I times mi, this weighted sum, and double norm is given by the summation of this mi, and kappa class, kappa m, the notation is kappa I mi, okay, so you have this is a characteristic class. We can then we derive the following recursion formula, which generalize Mirzakhani's formula. Okay. So remember, Mirzakhani only gave kappa 1, but here we have all the higher kappa involved. And it turns out that there's a similar, okay, a recursive formula satisfy the universal pattern, okay, as we mentioned. Okay. And here are the coefficient alpha can be explicitly calculated. Okay. So that's what we did. So that's the formula. Okay. Of course, the pattern is the same. Involve the same kind of class. If you involve more class, it will not be interesting, because you get tau and tau kappa everywhere. Okay. So that's similar. This coefficient also satisfies similar pattern, double factorials. So now we come to what we mentioned, the so-called super Riemann surface. A super Riemann surface, as defined as a Riemann surface equipped with a spin structure or a quotient of super hyperbolic space. So in our discussion, we will only consider a Riemann surface with a spin structure, because here see that it will involve a Dirac operator. So you want to take square roots for the canonical line bundle. Okay, so therefore, this moduli space for so-called spin Riemann surface, moduli space of Riemann surface with a spin structure is a finite cover over the moduli space of ordinary moduli space or ordinary moduli space. Okay. It turns out, but you get physically you get a new theory. It's kind of interesting. So there's a natural L2 inner product, okay, and which is a symplectic form. You get a volume form, so that's called Weil-Petersson volume, okay, and so you get a moduli space super Riemann surface with boundary component or length L1, L2, Ln. Okay, so you, again, the boundary is geodesics. Okay, so the geodesic length is uniquely determined, and you allow it to change. So in 2020, Stanford and Witten, they proved that such a volume is the integration of the Euler form holomorphic vector bundle combined with the Weil-Petersson symplectic form over a moduli space of spin hyperbolic surface. Okay, so here is what the moduli space of Riemann surface with boundary with spin structure, which is finite cover over ordinary moduli space with boundary. And this holomorphic vector bundle actually is the kernel of the Dirac operator, okay, on this moduli space. And you can see that the Euler class you combine with the Weil-Petersson volume, okay, form, and what you get is what they are interested from physical point of view. So here O00 represent the so-called Schwarz boundary, which is not used here. We reduce it to a mathematical calculation, okay, and so Dobry first constructed a theta class on MGN, so reduce everything to calculation on ordinary moduli space. But what he did is just to push forward the Euler class of Stanford Witten to the ordinary moduli space, which is just finite cover, push forward. And you put that class here, and you consider this is actually, this guy is just a symplectic class. That's a Weil-Petersson class on a moduli space on a moduli space for this with boundary. Okay, so therefore you can reduce to the calculation kappa 1 and psi classes together with a class from the Euler class of the spin structure. Okay. So therefore, the calculation of Stanford and Witten is reduced to calculation of this integral up to a constant. Okay. What? See the class, as I mentioned, is this Euler class pushed forward to the ordinary moduli space. So this guy is a finite cover of downstairs. We push it forward, so it's the same degree class. Yeah, and what he did is he showed that this guy satisfies certain kind of recursive property, and that's what he did. Yeah, and so this is the class. So this large genus asymptotic is very important for understanding so-called JT gravity, or super JT gravity. Actually, that's what Zhou reminded me yesterday. Non-perturbative structure. Okay, that's physics. This which seems to be quite hot topic in past several years in physics. Okay, there are a lot of works on this JT gravity, but mathematically we're just trying to calculate this integral. So there recursive formula derived from Stanford-Witten. So recursive formula is given by the following. We denoted by kappa b, as we introduced before, the product kappa classes is just equal to, you insert the theta class together with kappa class and psi classes together. Okay, so this recursion formula is given by, you can see that you can only get from Stanford or Witten, you get kappa 1. Okay, so like the ordinary case. So kappa 1 class to the power a, and the psi classes inserted, and then you get the same kind of recursive formula, okay, from what they did. And double factorials numbers, and beta b. Beta b is given by the expansion of 1 over cosine square root 2x, the coefficient. Okay, so therefore, double factorial is very similar to the previous formulas, and together with this coefficient different. Okay, but the universal pattern is still the 3 boundary component. Okay. So with student Fu Xu, Hao Xu, Yuxian Huang in Zhejiang University, we proved the following generalization of Stanford-Witten formula to higher Weil-Petersson volume. Okay, so basically we consider 2D plus 1 double factorial and kappa b. This involve higher kappa classes. So any number of kappa classes, not only kappa 1, and psi class inserted with this theta class inserted, you get this factorial, double factorial numbers and alpha L. And here the alpha can only be recursively calculated, okay, from alpha 0 equal to 1 from this recursive formula. Of course, this is more complicated than the previous formula. Okay, and this is all multi-combinatorial numbers. Okay, and so this is more complicated. Okay, and together with double factorial numbers, and of course the pattern of these intersection numbers are the same. Okay, as here, kappa also involve higher kappa classes, but with a less tau class or lower genus or lower genus to lower genus case. Okay, so that's the recursive formula we obtain. So the proof, we apply inversion operation to the superversion of DVV formula and the Kaufmann-Manning-Jackiw formula. So actually that means there's this push forward formula from previously in principle from as I mentioned, this Riemann surface. Yes, let me see. Oh. So let's chalk. So basically, and you have so you can see the modular space downstairs, and this guy is like a universal family, okay, with n+1 mark point. Okay, so say 1 plus 1. So this is MGN. So basically, you forget the n+1 mark point, and you get a point downstairs. Okay. And so this pi is this map. So we go reverse, and so we have this formula. Okay, and by using this formula, we can go back and to derive this formula. Okay. And here we can derive 4 recursion formulas together. Okay, by using the projection formula, we in the previous slides we can get this. For example, this involve only kappa class and no psi class. Okay, so here the volume of Gn, that means in previous integral. Okay, in the integral, there's no psi class. We only have a kappa class. Okay, so in that case, you get a simpler recursive formula. So you can see that only Vgn plus 1, n+1 mark point kappa b, and together with this this number, interesting number, and then you get Vgn kappa b. Okay, so you have less mark point, and you have that's marked point. Okay, so that's for the cup integral volume. And similarly, you have you multiply by the norm B and Vg kappa B. Okay? And this guy is given by you have the same G, but you have I think less kappa class. Okay, this guy is reduced. This guy is relatively reduced to make it smaller. Okay, so similarly, so you get this kind of recursive formula, which is some kind of new. Okay, so what we hope is we hope that these formulas, as before, okay, can be used to study asymptotics of higher Weil-Petersson volume. Okay, so actually, our previous formulas on the ordinary moduli space, we did get it's indeed applied to, for example, in geograph Marjakani's work, they can be used to study the asymptotics of these volumes. Okay. Okay, so I will stop here. I guess too fast.
Thank you very much for excellent talk. Is there any question or comment?
Oh.
Thank you. So what happens with the spin structures in the degenerations in the moduli space?
So it involves, it came in as a Euler class of the, you can see it's a kernel of the Dirac operator. So that means that's a finite cover. Okay, so this is, you have a spin structure. I think roughly speaking, so it's a finite cover over, and here you have a, you can consider actually here you have a, the H, I think you can identify it to H0, each Riemann surface over here, the family, or you can, universal family, and actually for each Riemann surface, say P, for example, okay, you consider K, say P, the canonical bundle, half to the power 3. So you need to take the square roots. You can identify to this space. So this is the vector bundle. You consider it's a Hopton class. Okay, and this, so the spin structure came in from here, and the theta class is the push forward of this guy.
You mentioned a Fundy's lattice point counting. Is that somehow related to Norbury's lattice path counting, lattice point counting? I think
Here?
Norbury has some kind of like he considered metric Riemann graphs, the moduli space of metric Riemann graph. Consider lattice point.
Yes, I briefly. We didn't consider that yet. I briefly went through and talked to Hao Xu. We didn't find the explicit relation yet. Yeah. So maybe we can talk about it later. Yeah. I know he has a lot of work. And also, actually, I know Peter Sanak, they wrote a book, I think, before, the counting lattice point, integer point in the moduli space itself, more P or something, yeah. Hunting point there. Yeah. So maybe, well.
The Norbury is just using a combinatorial model.
Combinatorial model of moduli space, the counting lattice point there.
Riemann graph.
Oh, Riemann graph. Okay. Well, say again? I don't know. We didn't consider that. Yeah, this is quite a new result. Our paper hasn't a super case. Yeah, we haven't go that far. There must be something there. Yeah. Well, the integer behavior. as I mentioned, I think somewhere, even for the spin case, as Jen Zhou talked about yesterday, this is all in the family of physical theory, or moduli surface of theory of physical theory. And this guy corresponding to, this aspect corresponding to R, so-called P go to infinity, P2, P go to infinity. I think I mentioned that somewhere, I don't know. Yeah, yes, you see, sometimes it's not, there's no, even for the R-spin case, it's very related. In the same family of series, this polynomial property, integer property, polynomial property fails. Yeah, we at least for R-spin case, only hold for R equal to 2 and 3. R equal to 2 is an ordinary case. So I'm not sure for the spin case. Yeah, you still have this integer phenomena.
Other question? If there is no other question, let's start speaker again.